In our previous video, we analyzed 1,771 CSIR NET previous year questions across all units and sections. That data showed one thing clearly: ecology is the highest priority unit, and most students are not approaching it the right way. This video is the first practical application of that analysis. Before we begin, I want to state the philosophy of this channel. The one principle that separates useful exam preparation from wasted effort. You do not need to solve thousands of random MCQs to crack CSIR NET. What you need is the ability to recognize the concept being tested, connect it to what you already know, and reason adaptively, even when the question is unfamiliar or morphed from a standard form. That ability does not come from blind repetition. It comes from working through a carefully selected set of questions analytically, understanding the why behind each answer, and building a framework you can apply anywhere. That is exactly what this video is designed to do. 5 ecology questions. 5 reasoning frameworks. Starting now. Question 1. This is from CSIR NET June 2016. 2 species, A and B, are competing. Species A has a carrying capacity of 150, and species B has a carrying capacity of 200. The competition coefficients are alpha equals 1.0, which measures how much species B suppresses species A, beta equals 1.3, which measures how much species A suppresses species B. The 4 options are: species A wins, species B wins, both reach a stable equilibrium, or both reach an unstable equilibrium. Pause here. Before reading on, think about what these numbers mean. Which species is under more competitive pressure? The correct answer is option B. Species B wins. Here is the reasoning. In the Lotka-Volterra competition model, the outcome depends on nullcline positions, not just carrying capacity. For species A to competitively exclude B, its carrying capacity divided by alpha must exceed B's carrying capacity. That gives us 150 divided by 1.0, which equals 150. But KB is 200, so 150 is less than 200. Species A cannot win. For species B to win, KB divided by beta must exceed Ka. That gives us 200 divided by 1.3, which equals approximately 153.8. And 153.8 is greater than 150. So species B wins. The key insight is this. Alpha equals 1.0 means species B suppresses species A exactly as strongly as species A suppresses itself. Combined with B having a higher carrying capacity, B always pushes A to extinction. The common trap is choosing stable coexistence. Coexistence only happens when each species limits itself more than it limits the other. That condition is not met here. Question 2. CSIR NET June 2016. A population of gypsy moths has an egg density of 160 at time t, and 200 at time t plus 1. Assuming the population increases at a constant geometric rate, what will the egg density be at time t plus 3? The options are 250, 280, 312, or 390. Take a moment. Identify the growth factor first, then apply it the correct number of times. The answer is option C, 312. Here is the method. When population grows geometrically, we use a constant multiplier called lambda. Lambda equals n at t plus 1 divided by n at t. That is 200 divided by 160, which equals 1.25. Now apply lambda from t plus 1 to reach t plus 3. That is 2 more steps. At t plus 2 to 200 multiplied by 1.25 equals 250. At t plus 3 to 250 multiplied by 1.25 equals 312.5, which rounds to 312. The most common mistake here is choosing 250, which is the population at t plus 2, not t plus 3. Always count your steps from the last given data point. The question gives you t and t plus 1. So t plus 3 requires 2 more multiplications by lambda. Geometric growth is not addition. It is repeated multiplication. Every generation, the absolute number added also increases. Question 3. CSIR NET June 2016. You are given population density data for 3 species. Species A has a mean of 5.30 and a variance of 5.05. Species B has a mean of 7.05 and a variance of 0.35. Species C has a mean of 5.30 and a variance of 50.5. Which of the following correctly classifies their distribution patterns? Option A says A is uniform. B is random. C is clumped. Option B says A is random. B is uniform. C is clumped. Option C says A is clumped. B is uniform. C is random. Option D says A is random. B is clumped. C is uniform. One number in this data tells you everything you need. Can you identify it? The correct answer is option B. A is random. B is uniform. C is clumped. The key is the variance-to-mean ratio. When variance approximately equals the mean, individuals are distributed randomly, following a Poisson distribution. Species A. Variance 5.05 is approximately equal to mean 5.30. Random distribution. When variance is much less than the mean, individuals are evenly spaced. Uniform distribution. Species B. Variance 0.35 is much less than mean 7.05. Uniform distribution. When variance is much greater than the mean, individuals cluster together. Clumped distribution. Species C. Variance 50.5 is much greater than mean 5.30. Clumped distribution. The trap in this question is thinking that a higher mean indicates more clumping. That is wrong. Species B has the highest mean but the most uniform distribution. The distribution pattern is about spatial arrangement, not abundance. Question 4. This is a CSIR net recurring pattern. It appears in multiple years. A population has a carrying capacity K of 1000, a current population size N of 400, and an intrinsic growth rate R of 0.3. Using the logistic growth equation, calculate the instantaneous population growth rate, dN over dt. Options: 72, 120, 48, or 84. Write out the equation before picking an answer. What term do most students forget? The answer is option A, 72. The logistic growth equation is dN over dt equals R times N times the quantity K minus N, divided by K. Substituting. R equals 0.3. N equals 400. K minus N equals 600. K equals 1000. Step 1. R times N equals 0.3 times 400 equals 120. Step 2. K minus N divided by K equals 600 divided by 1000 equals 0.6. Step 3. dN over dt equals 120 times 0.6 equals 72. The most common wrong answer is 120, which is simply R times N, ignoring the density-dependent term entirely. That term, K minus N divided by K, is the entire point of the logistic model. It represents the fraction of carrying capacity still available. At N equals 400, only 60% of carrying capacity remains. So growth is reduced by 40% from its theoretical maximum. Never drop that term. It is what separates logistic growth from exponential growth. Question 5. Another CSIR net recurring pattern. In an aquatic ecosystem, the biomass pyramid is inverted. Phytoplankton, the primary producers at the base, have lower standing biomass than the zooplankton above them. Which of the following best explains this? Option A. Phytoplankton have much slower turnover than zooplankton. Option B. Phytoplankton are heavily grazed despite high productivity. Option C. Zooplankton have lower assimilation efficiency than phytoplankton. Option D. Phytoplankton primary productivity is lower than zooplankton secondary productivity. Think carefully. This question tests whether you understand the difference between two related but distinct concepts. The correct answer is option B. Phytoplankton are heavily grazed despite high productivity. The concept being tested is the difference between standing crop and productivity. Standing crop is the biomass present at any moment. Productivity is the rate at which biomass is produced. Phytoplankton in aquatic ecosystems divide very rapidly, sometimes in a matter of hours or days. Their productivity is very high, but they are also consumed by zooplankton at a very high rate. The result is that very little phytoplankton biomass accumulates at any given time. Zooplankton, by contrast, live for weeks or months and are grazed more slowly. Their biomass accumulates, so at any snapshot in time, zooplankton standing crop exceeds phytoplankton standing crop, even though energy flows upward from phytoplankton. Option A is the opposite of reality. Option C and D describe mechanisms that have nothing to do with the inversion. Whenever you see an inverted biomass pyramid question, the answer always connects back to turnover rate and grazing pressure. Those were 5 ecology frameworks from CSIR NET for Lotka-Volterra Competition. Compare K over alpha and K over beta. The nullcline positions, not gut feeling, decide the winner. For geometric population growth, always find lambda first, then multiply the right number of times. For distribution patterns, the variance-to-mean ratio is your diagnostic. If you remember nothing else, remember, greater than 1 is clumped, less than 1 is uniform, approximately 1 is random. For logistic growth, never drop the density-dependent term. If you write Rn alone, you are solving exponential growth, not logistic. For biomass pyramids, standing crop and productivity are not the same thing. Turnover rate is why an inverted pyramid in aquatic ecosystems makes perfect sense. These are not just answers. They are templates you can use every time you see any ecology question built on the same concept. Now, a quick preview of what is coming next. Our PYQ analysis identified structure and function of biomolecules as the single largest CSIR net unit, with over 11,000 questions across the database. That unit is next in this series. 5 biomolecule PYQs. 5 reasoning frameworks. Same structure, same depth. Subscribe to this channel so you do not miss it. And if you want to practice ecology or biomolecule questions right now, visit gekjrfacademy.com. The link is below. See you in the next video.